All right, guys. Right now, make sure you're open to page 21 in the packet, which is the parallel axis theorem. Now, we've already come up with how to find a moment of inertia. And most of the time, unless you're going to have a bunch of separate little bodies there, excuse me, you're going to be able just to look up moment of inertia on a chart. But those moment of inertias are all for if the axis of rotation goes through the center of gravity of the object. Now, what about if the axis of rotation is off from that? If it's not going through the center of gravity for that object? Well, we can find the moment of inertia by using something called the parallel axis theorem. And basically, it says this. Your new moment of inertia is equal to the moment of inertia going through the center of gravity plus the mass times the distance between where your moment of inertia through the center of gravity is and your new moment of inertia axis, which in this case we're going to use just a plain old rod. Let's think about a rod, okay, where you're going to have the right through the center of gravity have your axis rotation. The moment of inertia for that rod is going to be equal to, let's get this right, I equals 1/12 ml squared. And make that capital M because we're going to be calling this thing have a mass of capital M. Now, what we want to do is we want to solve for the moment of inertia with the axis of rotation through the end of the rod. So this is our new axis right here. Our axis to the center of gravity, CG axis, which means if the whole rod's got a length L, that means D is going to be equal to L over 2. Okay, that's easy enough. Now let's take a look at it. Flip the page over, and we'll show you how you put this all to good work. Get this to work out for you. All right, and we got that written right on the top there. You know that your moment of inertia, this is the new one, is going to be equal to I through the center of gravity plus md squared. That's the parallel axis theorem. As long as the axes are parallel to each other and you've got the moment of inertia going through the center of gravity, you can get your new one. I is equal to, well, we know this is 1/12 ml squared plus m, and that distance was actually going to be equal to L over 2. And we're going to square that. Now, that becomes 1/12, ml squared plus m, that becomes L over 4. And the L is squared. 1/12 ml squared plus, just neaten it up a little bit, 1/4 ml squared. Add them together, and I turns out to be 1/3 ml squared, which if you take a look back on our chart before, and I'll just flip right back to it where it was, it turns out, here it is, (1/12 ml squared. If it's off on the end, it's 1/3 ml squared. Works out perfectly. Now, another nice thing about all the equations for rotational motion is that they correspond precisely to the linear motion equations. For example, your linear position is your average velocity times your time. Your angular position is your angular velocity times your time. Final velocity equals your initial velocity plus acceleration times time. Final angular velocity equals your initial angular velocity plus your angular acceleration times your time. And you can look up and down the chart and you'll see that every single one of the linear motion equations has its corresponding angular motion equation. That makes your life much, much, much easier. pause the video right now and look them through, make sure it makes sense to you. Okay, change to page 23, and that is going to be dealing with rotational dynamics and torque. Now, we already know that F equals ma from Newton's second law. Well, there's a rotational version of Newton's second law, which is your torque is equal to your moment of inertia. Remember, we think about like rotational mass times your angular acceleration. That's an alpha. Or the sum of the torques, or the net torque, equals I alpha. Let's take a look at this. As an example, I've got a 20 kilogram solid disc with a radius of 0.2 meters, has a rope with a constant force of 10 newtons acting on it. Find the angular acceleration of the disc. Here's our disc. Here's our force. Now, let's keep one thing in mind. Anytime you've got a force or a rope coming off of a disc, that means that you're going to wind up having this thing come off tangent to the circle. The force is tangent to the circle. Makes life a lot easier. If I draw a radius there, it's going to be perpendicular. All right, and it's already written there. So let's apply Newton's second law, but rotationally. Now we're going to set a direction for positive for this thing, and I'm going to call this thing rotating in that direction as positive. I know that is the direction for the convention, but we're not always going to stick to that because sometimes it's actually easier to call the other direction positive, and we'll get to that in a second. So basically, my torque equals I alpha, or if you want the sum of the torques equals I alpha. The only thing causing a torque is the torque from that force, and it's creating a positive torque. We hold on to this and we turn it in the direction based upon the direction that we decided to call positive here. We're going to call that guy positive. So anyway, torque from that force is I alpha. We know torque is going to be RF, and we'll write the sine theta, but really we don't need it because it's 1. It's at 90 degrees. Okay, we know that I for the solid disk is 1/2 mr squared times alpha. Now here's where things start to get nice. We can start crossing out one of the radii. We're all set with that. So let's play around with this algebraically. If I bring the half over and divide by mr, that becomes 2 times my force over mr is equal to alpha. So that's going to give me 2 times 10 newtons times my mass, which is 20 kilograms, times 0.2 meters equals alpha. That is 5 newtons per kilogram times meter is equal to alpha. I just carried all the units through. Let's go up to the top here. Let's deal with those units. We know that a newton is a kilogram meter per second. Squared, excuse me. Kilogram meter per second squared divided by kilogram meters equals alpha. Well, that drops out. That becomes 5 times 1 over second squared equals alpha. Now remember, we said radians is kind of like a non-unit. So we could actually throw it in here just to make more sense out of it. 5 radians per second squared equals my alpha. All right, flip the page over. Let's take a look at another example. A disc with a mass of 2 meters and a force of 10 newtons applied to the center of the disc towards the right. If the disc is frictionless, draw the free body diagram and determine the acceleration of the disc. All right, the disc is frictionless. So it says that I'm going to have a force applied to the right of 10 newtons to the center of the disc. Okay, now even though we may not need them, free body diagram, you must draw all the forces. So you know that you're going to have force of gravity. I just write mg for the force of gravity. You guys get that. And acting upwards, there will be a normal force. That's it. Now the first part of this is actually really, really very, very easy. All we've got to do is sum of the forces equals ma in the x direction. It's not going to even rotate. There's no torque on this thing. And it's simply going to be force equals ma. You've got a 10 Newton force on here. Your mass is 2 kilograms. And you want to find your acceleration. Your acceleration is going to turn out to be, of course, 5 meters per second squared. Now let's ratchet it up a bit. Now we've got the same disk moving to the right without slipping. Let's find the acceleration of the disk. If it's not slipping, okay, that means I may be pulling on it to the right here with my force of 10 newtons, but acting backwards at the point of contact is going to be a force of friction, right? It actually would start rolling like that along on the ground because of the force of friction. Of course, we do have our force of gravity acting downwards on it, and we've got our normal force acting up on it. Next thing we want to do is we want to find out, well, how fast it's going to move. This time you can't ignore torque because this force of friction is going to make the thing start to rotate like that. I'm going to cheat a little bit. There's my x, there's my y. I'm going to consider those guys positive. And because it's going to wind up turning in that direction, I'm going to consider that direction positive for my torque. Yeah, I know the convention's the other direction, but this just makes life a lot easier as we work this all the way through. It keeps everything all positive. Means that the acceleration is going to be actually positive. It really doesn't work out that way if you're really technical about it, because the body moves this way, and because it rotates like this, you'll actually get a negative linear acceleration at that point on the bottom. But just switching around the direction you call for positive makes life much easier. So here we go. Okay. Now, also keep in mind these two do not equal each other. Otherwise, the thing wouldn't even move, right? It wouldn't start to accelerate. So force and force of friction don't equal each other. So we're going to now start out just like before. Sum of the forces equals ma, and that's going to be in the x. Now you're going to get your force minus your force of friction is going to be equal to your mass times your acceleration. That works out pretty nicely. And let's put an S there because it is static friction. The thing's not sliding. You don't know what the force of friction is. So you can't really work out what the acceleration is. However, we do know this. Sum of my torques equals I alpha. My torque, caused by my force of friction static, is equal to my I times alpha. All right, it's a solid disk, so that solid disk is going to wind up having an acceleration, a moment of inertia of 1/2 mr squared. Your torque is going to be equal to R times that force of friction static, and we get that times alpha. Now, just like we said before, we can relate the linear acceleration along the edge of that disk to its angular acceleration by alpha equals A over R. So we're going to do that right now. R times my force of friction static equals 1/2 mr squared A over R. Drop the squared, drop the r's, and now we're left with this. Which works out beautifully because we can take this and slip it right into here for my force of friction static. My force minus my force of friction static is equal to, oh, sorry about that. I want to do that substitution. 1/2 ma equals ma. Put them together. My force is going to be equal to 3/2 ma, or my acceleration is equal to 2 times my force divided by 3 times my mass. Pretty easy to solve it now. My force was, what did we say that was? 10 newtons. 3 times my mass. My mass was going to be 2 kilograms. And that turns out to be 20 divided by 6, 3.33 meters. Whoops, sorry about that. Meters per second squared. Sorry, I didn't realize I was off the screen there for a second, but you guys should be okay with that. All right. So far, so good. Now, let's turn to the next page, and that's the Atwood machine. Now, we've done this before. The only thing that's different is that when we did it last time, the wheel had no mass to it. It was light. Now the thing's got mass to it. So do both of these blocks. So we're going to first of all set a direction for positive along the rope. Considering that block is more massive than that block, I'm pretty assured that this thing is going to wind up rotating in that direction. So let's call this positive along the rope, which calls this guy positive here, this guy's positive there. Now everybody's got the same accelerations. Okay, we should all be nice and happy with that. Let me just slip something underneath here so I can write a little bit better. Okay, so set a direction with positive along the rope. Okay, don't change it. Now, guys, let's consider the direction of positive for each one of these bodies. That's positive there. That's going to rotate. It's positive there. And that guy's positive in that direction, based upon setting positive along the rope. We're now going to do a Newton's law analysis for each body. Well, of course, if I do the free body diagram for this guy, I'm going to have m of a times g down, and tension on A going up. That's one thing I should have mentioned a little earlier. Because this guy requires a torque for this to accelerate, you don't get the same tension on both sides. If you did, there'd be no torque on this thing wouldn't accelerate. So I'm going to call that tension of A, and this side tension of B. So this guy, as we work this through, I have sum of the forces equals MA. That means that I'm going to have MAG minus my tension from A is going to be equal to M of A times A. I'm going to rearrange this thing so I get tension of A out of it. Is equal to, and that's going to be MAG minus M of A times A. And that's as far as we can go with this. Now let's take a look at the other block. Flip the page over. Remember, this block we considered C to have positive upwards. Now, we have very similar forces. We'll have MC of G acting downwards, and we're going to have acting upwards, tension acting, and we'll call that tension B. All right? So, let's go through this thing. Sum of the forces equals mass times acceleration, and that's mass of C. So I get my tension B minus mcg, because it's in the negative direction, equals mass of c times my acceleration. So far, so good. Now, let's finish this guy up. Let's set it equal to tension of B. Plus, be careful, mcg. The signs are the killers on this. Absolutely. Now comes the point where we start to pull everything all together. The rotating disc. Now, we considered that way to be positive for this. You're going to have acting downwards, tension of A, acting downwards here, tension of B, action-reaction, okay? The tension's pulled up on the blocks and pulled down on the pulley. Now, even though we're not going to use it, there was some force holding this thing up in the center. Now that we're all set with this, here we go. Sum of the torques equals I alpha. All right. Now, this thing's a solid disc, so I'm going to get two torques. I'm going to get the torque from the tension of A minus the torque from the tension of B. They're in opposite directions, equal to I alpha. Now, we know that our I is going to be 1/2 mr squared. It's a solid disk. So the torque from A minus the torque from B is equal to 1/2 m of c r squared times alpha. Now, as we've been doing all along, torque from A minus the torque from B, or that should be tension of A, torque from the tension of B, tension of A, tension of B, is equal to 1/2 mc r squared, and they're going to put in A over R for alpha. Now, torque is R times the force. So I'm going to get R times the tension of A minus R times the tension of B is going to be equal to 1/2 mass of C R squared A over R. And now a beautiful thing happens. This R cancels out those squares, and all these R's go away. Makes life much, much, much easier. Now remember, in the other side, we did our tensions and set up all our equations so they were equal to tension. So we can drop them in right here. From the first part, we knew that tension of A is equal to mass of A times G minus the mass of A times A minus the tension of B. Let's put a parenthesis on this because we tend to screw up our signs right now. MC of A plus MC of G, right from the top of the page, that's tension of B, equals 1/2 MC times A. Let's deal with those parentheses. MAG minus MAA minus MCA minus MCG equals 1/2 mass of C times A. All right. Break out your algebra thinking caps because we're going to start playing with this. We want everything with an A, with acceleration on the right-hand side, everything with gravity on the left-hand side. So, here's my, oops, made a little mistake there. Let's get that, straighten that out. Okay, these are the only two guys with G. So I'm going to pull the G out of it. That's strictly coming from those two guys. Now I'm going to bring this onto the other side. All right, and I'm going to pull the A out of each of these terms. So that's going to be A times mass of A plus mass of B plus 1/2 the mass of C. Let's combine everything. All right, now that that's all set, all we got to do is shove in the numbers, and we're going to be good. Well, let's let g equal 10 meters per second squared. It's 9.8, but we'll, just to be nice to ourselves, we'll do that. Okay? And so, we know that the mass of A was 10 kilograms, plus the mass of C was 2 kilograms. All that over my mass of A, which is 10 kilograms, plus 2 kilograms, oops, didn't need a parentheses that, plus 1/2 of 10 kilograms. Work that whole thing out, and you end up with about 3.6 meters per second squared. Okay? If you need to, stop it, rewind it, look over the whole thing again to make sure that it makes sense. All right. Finally, the last part on this is a ball rolling down a hill. Now, the ball's got a radius of r and a mass m, and we want to find out what is going to be its acceleration when it hits the bottom. Now, we're going to make this a solid ball, which means the moment of inertia for the solid ball is 2/5 mr squared. All right, keep that in mind. It's a good time to be running out of lead, but we'll make it through here. So first thing we want to do is we want to draw mg going down, normal force going this way, mg sine theta, because our theta is right here. And just 1 second, let me grab another pencil. There we go. We know that we're going to have acting backwards on this thing. That worked great. Force of friction. And of course, you get that normal force. I marked it in, but I didn't draw it. There's my normal force acting up. We don't have to worry about mg cosine theta here because we're not having any accelerations in that direction. And friction, we're not hitting maximum static friction. Oh, sorry about that. Once again, let me show you again. mg is acting down, mg sine theta in this direction. We're not going to worry about mg cosine theta. We're not going to have to worry about in the vertical direction. We draw the normal in because it's the right thing to do if we're doing a free body diagram. And the force of friction acts backwards in that direction. Now keep in mind, mg sine theta is not going to create a torque. It really acts right at the center. Even though it's down here in the drawing, it's all acting on that point. The only thing that's going to create a torque is the force of friction. So, sum of the forces equals mass times acceleration. Now we have acting positively, mg sine theta, because let's set our directions for positive. There's my x. It's a great pencil. There's my y. And this thing's going to rotate like this, so I'm going to consider that direction positive. It's just going to make everything positive and makes things work out easily for us. mg sine theta minus my force of friction. I think we've had enough with that pencil. Okay. mg sine theta minus the force of friction is equal to my mass times my acceleration. Can't really go much further than that. Let's deal with the torques. There's only one thing. Sum of the torques equals I alpha. And there's only one thing creating a torque. And that's the torque that's being created by the force of friction. Equals I alpha. Now my torque from the force of friction is going to be equal to my radius times my force of friction. Now remember, we said I was 2/5 mr squared. And we've done this often enough now. R alpha equals my acceleration divided by r. Goodbye r's. So my force of friction is 2/5 ma. This now can go up into there. And I'm just going to bring this down a bit so that I've got a little more room. mg sine theta minus 2/5 ma equals ma. Bring this over. Well, first, masses all drop out. That becomes g sine theta is equal to, let's bring this on the other side, 7/5 a, or my acceleration turns out to be 5/7 g sine theta. But we want to find the speed at the bottom. Well, not a big deal. Vf squared equals v naught squared plus 2a times, I'll make it delta x. You could put d in there, whatever. It's going to wind up being that L going down the length of the incline. Initial velocity starts at 0. V final squared equals 2 times my acceleration, which is going to be 5/7 g sine theta, times L. Do the math. This becomes 10/7 g L sine theta, square root of the whole thing, turns out to be my final velocity, and we are all set. Okay? Thank you very much for watching. I'm sure you had to pause it a lot going through, but hopefully this gets us all caught up. Take care.